This is going to be the final lecture of Physics 1. We'll be going over Chapter 20, Entropy and the Second Law of Thermodynamics. Okay, so if an irreversible process occurs in a closed system, then the entropy, which is written as capital S, of the system always increases. It never decreases. So let's take a look here. So we have our system here, we have some insulation, we have a vacuum. If you take this stopcock and pull it up and allow the gas to go from one to the other, there's really no way to take this and to put it back. That's why we consider it to be irreversible. Also, if you look over on the right side, you've got thermal reservoir, you've got insulation, you've got lead shot, you've got a control knob. So depending on how high the temperature is there, you can see how much volume is taken up by the gas. If heat ends up escaping, then you can also see here that this process can go back to what you see here. So it's considered to be reversible. So obviously, as you've probably guessed up to this point, the process over here is irreversible. That, in other words, it does not occur in reverse, with the gas spontaneously collecting itself in the left half of the container. The isothermal expansion of an ideal gas is done in a reversible way. So if a process occurs in a closed system, then the entropy of the system increases for irreversible processes and remains constant for reversible processes. So if we're going to look at the change in entropy, and you're not going to calculate the actual final and the actual initial unless they're given to you, because in many ways they're just meaningless. But the change in entropy is going to be the integration of the infinitesimal portions of heat that are added divided by the temperature. So here Q is the energy transferred as heat to or from the system during the process, and T is going to be the temperature of the system in kelvins. So to find the entropy change for an irreversible process, replace that process with an irreversible process that connects the same initial and final states, and then calculate the entropy change for this reversible process with this equation. So if a process occurs in a closed system, the entropy of the system increases for irreversible processes and remains constant for reversible processes. It never decreases. So what this second law is going to say is that the change in entropy of a system is going to be greater than or equal to zero. It's never going to be less than. So the greater than is going to come from the fact that you might have irreversible processes in the system. The equal sign comes from the fact that you are going to have reversible processes. Okay, so engines. In an ideal engine, all processes are reversible and no wasteful energy transfers occur due to, say, friction or turbulence. That's ideal. So if you take a look here at the pressure volume plot of the cycle followed by the working substance of the Carnot engine, the cycle consists of two isothermal, A to B and C to D, and two adiabatic processes. The shaded area enclosed for the cycle is equal to the amount of work per cycle done by the Carnot engine. So you've got here your isothermal processes and then your adiabatic processes. And then you can follow these processes as they go around. And you can see the isothermal, that heat is absorbed and then positive work is done. Adiabatic processes going from here to here where there's no heat added. But what you're looking at here is that positive work is in fact being done, and heat is actually entering the system. Here you are seeing that negative work is being done. You can see that because the arrow is pointing this way. And then isothermal heat is being lost. So since this is an ideal engine, the amount that goes in and the amount that goes out should be the same. So if you take a look at the schematic, you've got temperature of the heat that is being added. And then you've got the heat that's being absorbed, and then you've got the work, and then you've got the heat going out. So the elements of the Carnot engine are displayed here. The two black arrowheads on the central loop suggest the working substance operating in a cycle as if it's on a PV plot, just like what we just saw. So no series of processes is possible whose sole result is the transfer of energy as heat from a thermal reservoir and the complete conversion of this energy to work. So you've got the efficiency of the Carnot cycle, where you've got the energy that you get out, which you can use for work, and then the energy that you pay for. And therefore, if you go through and you calculate it out, you can see the efficiency of a Carnot engine is going to be 1 minus the temperature of the low area divided by the temperature of the high area. So you can see here the elements of a perfect engine. That's one that converts heat, Q sub H, from a high temperature reservoir directly into work with 100% efficiency. The elements of a Carnot engine, you can see here, the two black arrowheads on the central loop suggest the working substance operating in a cycle. So you can see the heat coming from the reservoir, you've got it going out, and the engine's doing work, and then you've also got some heat lost. Now the Stirling engine was developed in 1816 by Robert Stirling. It's been neglected, but is now being developed for use in automobiles as well as spacecraft. You've got the PV plot over here on the right, and this is for a working substance of an ideal Stirling engine, with a working substance assumed for convenience to be an ideal gas. Okay, so you've got 3 Carnot engines that operate between reservoir temperatures of 400, 500, 600, 800, and 400 and 600. To rank the engines according to their thermal energies greatest first. So in other words, you've got the lower temperature here and you've got the higher temperature here. If you go back and use this particular formula, you can calculate the efficiencies. And when you do that, you can get the answers in that order. So in an ideal refrigerator, all processes are reversible and no wasteful energy transfers occur as a result of friction and turbulence. So again, this is what you want. You want Q sub L, what you pay for is the amount of work. So the coefficient of performance is defined as such. And this is for a Carnot refrigerator. This is going to be for any refrigerator. So here you've got a perfect refrigerator, total transfer of heat from cold to hot without any work. Over here, of course, you've got the heat that's being absorbed, you got the work that you wanted to do, and then the heat is lost out here in the high energy region. So the entropy of a system can be defined in terms of the possible distributions of its molecules. For identical molecules, each possible distribution of molecules is called a microstate of the system. All equivalent microstates are grouped into a configuration of the system, and the number of microstates in a configuration is going to be the multiplicity of the configuration. So for a system of n molecules that may be distributed with between the two halves of a box, the multiplicity is going to be given by this. N sub 1 is going to be the number of molecules in one half of the box, N sub 2 is going to be in the other half, and the basic assumption of statistical mechanics is that all microstates are equally probable. In other words, one microstate is not going to be favored over another. So here, you've got the multiplicity of configuration. An insulated box contains 6 gas molecules. Each molecule has the same probability of being in the left as it does in the right. And the arrangement in A corresponds to configuration 3 in this table. And if you look at B, it corresponds to configuration 4. So you can see configuration 3 here. And then you can see configuration 4. So you can see the entropy produced here, and then you can see the entropy produced here. So the multiplicity of a configuration of a system and the entropy of the system in that configuration is going to be related by Boltzmann's entropy equation as follows. Here, the K is going to be the Boltzmann's constant. When n is very large, we can approximate the natural log of n factorial with Stirling's approximation, which is this. I've actually gone through some problems there using that. It does come in handy because you start to see exactly how large some of these macrostates can end up being. So here's the summary of everything we've gone through. And I do hope you have enjoyed the course.